Hello everyone. Welcome to circuit analysis for analog designers tutorial 5. So this week we in the main lectures we looked at the finite bandwidth effects on biquads. So we will revisit that and try to do try to do some simulation examples to actually test and visualize this concept. So let's begin with revisiting of the Q enhancement issue that we learned in the class. So the issue was as follows. So we had a op-amp that was a non-ideal one. So this op-amp was a non-ideal op-amp with a transfer function of omega u by s. Please, if you don't have any doubts within the lecture, you can mute yourself. If you have any doubts, you can raise your hands and I will let you speak. So kindly mute yourself while the class is going on. Okay, so where we were, omega u by s was the transfer function that we had for the op-amp. Now this transfer function was Talpasai, can you please mute yourself if you don't have any doubt as far right now?
Sure, sir. Sir, can you hear me, sir?
Yeah, I can
Sir,
hear you.
I'm following your lectures from week 1 onwards, sir, through recordings.
Okay.
Sir, I have if you give 1 minute means if I'm right path or not, I would like to know, sir.
Okay, sure. You can ask whatever doubt you have.
Yes, sir. In previous week, sir, can I share the assignment solution, sir?
Okay, you can share it.
Is there any way, sir?
Sorry?
Can
Are you
with you,
not
sir?
able to share it?
Can I share the assignment solution with you, sir?
No, you can
No,
share
sir.
the screen if you want. Do you
Yes,
want
sir.
to share the
I
screen?
mean, yes, sir. If you permit me.
Okay, sure. Share it.
How, sir? I'm not getting it's open in Google Chrome. Sir, if you
Uh,
want means I will send in a.
just see, can you do it now? I have added you as a co-host. I think now you can do it.
Okay, sir. Means it is very little, sir. Your screen is visible that your
Uh,
name and my name is very small, sir. Eyesight also.
now I think you should be able to. No, you don't need to open your camera. You need to share the screen. So if you go to this the three dots thing, either you will have a rectangle with an arrow in it. From that,
Yeah, this one,
you
sir.
can share your screen. I cannot see your screen right now, but yeah, if you there should be a rectangle with an arrow in it. If you click on that, there will be option of sharing your entire screen. Yeah, now your screen is shared.
Okay, sir. Sir, this one, sir. Week 4. No, week 5 I have, sir.
Okay.
I followed your procedure, sir. Can you see, sir? If I commit any mistake, please I will rectify it.
So, what was the exact problem that you were working on?
it's butterworth filter order
Sorry,
6.
come again. Yeah, you were trying to make a Butterworth filter with order 6. Okay.
Yes, sir. From means from week 3 lecture onwards, I how that Butterworth approximation came. From that I started, sir.
Okay.
Sir, is the correct way only, no, sir?
Yeah. Basically, you try to approximate the magnitude response. From that, you get a polynomial in S, and you will get
Yes, sir.
okay. Basically, you will get three cascades of second order sections, and some
Yes,
q
sir.
you will get. So q will be 1 upon 2 cos 2 pi by whatever order you need, right?
Yes,
And
sir.
so from there
This one, no, sir.
you get.
This one, no, sir.
So yeah, this is basically the one of the sections. Now here you have to decide the queues, and
Yes, sir.
so how you have decided the queues for sixth order Butterworth?
Means based on the for first order means for bicode one, I decided according to this, sir.
So for over first you have to decide the queues for all of the all of the
Yes, sir.
bipods, right? Yeah.
Yes, sir.
So
For bicode one, it is 707, sir.
this is the okay. How do you know this should be the bipod one?
Means we get approximation, no, sir, as s square plus s by 0.518 plus 1 s square plus 0.707 plus 1.
Okay,
This three
so
cascaded will get a sixth order.
correct. You can have any of these quality factors in the as the first bipod, right? Why any specific
Yes, sir.
reason? Why did you choose 0.707?
And for first one I choose 0.07, sir. For second one I choose point 518.
Yeah, that's
I
what.
means
Any specific reason for that?
specific reason means previously for fourth order I seen, sir. For that you design 0. Means you came the QR as first one as 0.707. That's how I did, sir. Means if you cascade
So
ultimately you'll get a sixth order,
yeah,
no,
so
that's
I
how I
will.
think, sir.
That's what. It's correct that like if you see an ideal system, there the order of the quality factors don't matter, right? Like you can cascade 0.707 first, 0.518 first, or maybe the last one 1.92 or something. So you can put anyone first, but in practice, we when you cascade these things, the order that you have actually does matters. So, do you guys know the procedure behind setting the setting the arrangement of stages?
So next, with this for bike code one, sir, this how I calculated the resistance, and I
Okay,
recalibrated the.
okay. So you just tell what all you have done, then we will see from there. So
Yeah, sir.
yeah,
This is for bike code one, sir.
so this is for bicod one. Okay, okay. So
I
this is
do. I did
dynamically
the
dynamic scaling is done.
yes, sir. Yes, sir. Exactly, sir.
Okay.
For this is the sir for bike code one. What and all the values I get, I put it in the circuit diagram, sir.
Okay.
This is
Next,
for bike
what did
code
you
two,
do?
sir. Bike code two, sir.
Okay. So input
And
resistance you took as what? Input resistance you took as what?
input resistance they given also in that question itself 10 kilo ohms.
10 kilo ohm for each. Okay, fine. Fine.
Hmm. So for bicod 2, sir, bicod 2 quality factor will change, no, sir. That's how I
Okay.
change.
Okay, 0.518 you had, fine. I will comment on this later, but yeah, go ahead.
Yes, sir. This is the circuit diagram, and you said no, sir. I called zero dB. You said a concept what you thought I get exactly, sir. But while designing, I'm not able to exactly fit. While that one parameter I am able to achieve, sir.
So did you plot the magnitude response of this complete cascade?
Complete cascade I'm not able to, sir. For for backward one I achieved what and all procedure I achieved the response, sir. Bike magnitude response.
Uh, okay, so you should.
That
So
is
what is
zero.
the
That
bandwidth?
is less than 0 dB.
No, no. What is the bandwidth? What is the bandwidth that you were supposed to get?
Yes, sir. Yes, sir. It is up to 0 to 50 kilohertz, sir.
50
Frequency range.
kilohertz, and
Yes, sir.
so so
I changed
have
it
you seen
to
that? No, no. Have you seen that at 50 kilohertz you are getting 3 dB 3 dB magnitude response? Have you verified it?
no, no, sir. That one I am not getting, sir.
You are not
I
getting it.
tried many times. That yes, sir. My dynamic range scale is not. That's how I get failed, sir. That's why
Okay, so
where did I
so
commit a mistake, sir?
is this assignment done? Is this assignment already
Done,
deadline
sir.
is over,
Done,
or
sir.
this assignment
Deadline is over, sir.
deadline is over?
Over, sir. Week
Okay,
five, sir. Deadline is.
okay, so we will go through this question once then. So let me
Yes, sir. Can I
take out
screen,
the.
sir? Okay, you would like to see?
Okay, I will share my own screen and
Yes, sir.
take this question.
Mm.
So this is week 4, right?
Yeah, sure, sir. Thank you, sir. Week five, sir.
No, this assignment is from week 4, right? This is the
Week
week
five,
4
sir.
assignment, right?
No, no, sir. No, no, no. Week five, sir.
So
Means
just a
week
minute.
six is now going to happen, sir. Week five is completed.
And the deadline is due on 3rd March. Today is so today only the deadline is there, right? So we should wait till the deadline
No,
is
no,
over.
sir. Deadline is over, sir. Already. It is week five, sir.
That's what deadline is till today 12 p.m.
No, no, sir. From within minutes, say deadline is completed, sir. First.
No, that's what I'm saying. Like the due date was okay. Okay, so it has passed. Okay, fine.
Yes, sir.
Uh, okay,
I mean, I
so
put my
this is the first
sir.
question.
That's why I followed your lecture. Uh, that's how
Just a minute.
even I have me.
So this is the so we need to design a low pass Butterworth filter. So this is the question that you are talking about, is it? Or week 5?
Week, week five, sir. Yeah, this one, sir.
So the first question.
Yeah, sir. In week four, I commit a mistake, sir. That DC game, I get an inversion, sir. If I following your recorded lecture, you interchange that integrated inverting terminal. I watch your lecture, sorry. While changing that inverting terminal towards at the output side, that DC gain sign will get changed, no, sir.
Yeah, correct. So that's what I showed, right? You can put that
Yes, sir.
inverter before that or after that. Based on that, the
Hmm.
DC gain at the output will change.
Yes, sir. In week four, I commit a mistake, sir. What I thought, while putting one more inverting terminal, then only that DC gain will get changed. I rectify that mistake and I put in on week five, sir. But I am not able to achieve that dynamic range scaling. I'm not able to achieve, sir. Within that
Okay, we
within
will.
that frequency range, sir.
Okay,
Here
we
that
will work
frequency
on
range
that.
only we have to follow now, sir. within 0 to 50 kilohertz frequency range only we have to
No,
plot, right, sir?
overall, you should achieve a dynamic range where all the peak. So dynamic range scaling is all the peaks of the all the peaks of the frequency response at each node should go to 0 dB. That's how you have to achieve the dynamic range scaling. We will okay. We will do this question here over here.
No, sir. My doubt is while you're designing, you mentioned that start frequency and start frequency. Mention that frequencies, sir. We have to start with according to that frequency range, zero to
That's what I'm telling you. Should while dynamic range scaling, what you have to do is you have to check check each of the nodes, and at each of the nodes you should have at each of the node you should have the maximum frequency response less than 0 dB. It's not only in the bandwidth; it's across the frequency range.
Yes, sir. You continue, sir.
Okay,
You
so
continue the question.
we will try to go through this question. So, is my screen visible?
Yes, sir.
Okay. So, what we needed to do, we needed to design a sixth order Butterworth low pass filter as a cascade of active RC sections satisfying following thing. Magnitude of DC gain of each biquad should be 1, and input resistance of each biquad should be 10 kilo ohms, and 3 dB bandwidth of the filter should be 25 kilohertz. Okay. And after that, determine quality factors of biquad. How will you order them? Assume ideal op amps and show the component values. Yeah, okay. Simulate the filter entry spice so that the frequency response at all nodes over 0 to 50 kilohertz, and verify that peak magnitude of all op amps output is 1. So this we are to do. Okay. So we will start with finding the quality factors. So we discussed previously, how will we find the quality factors? The quality factors of the biquads can be found by the following equation. So it's 2 pi by, wait, it's cos 2 pi by 4 for second. So it's so this is the equation with which you find the quality factors. So like the first one will be so n over here is so n is basically the 6 over here, correct?
Yes, sir.
So what we get is 1 upon so one of the quality factors will be 1 upon 2 cos pi by 12. Other will be 1 upon 2 cos 3 pi by 12, and the final one will be 2 cos 5 pi by 12, correct? So can someone tell the values of these numbers? So this will be 0.707, as it is 1 upon 2 cos pi by 4. Pi by 4 is 1 by root 2. So this is 0.5 something. Can you tell the precise number?
Yes, sir. 1 minute. Point. Sir, 0.518.
0.518.
Yes, sir.
And this one? 1.9 something.
932. 932, sir.
932.
Yes,
Okay.
sir.
So these are the quality factors. So the first question is, how will you order them? So how do you order them? Let's say we make these biquads. So this is biquad 1, then biquad 2, then biquad 3. Okay. So let's say we put this quality factor over here as the first one. What will happen in that case? This is the quality factor is 1.932. So what kind of frequency response do you expect? The magnitude response do you expect from this kind of quality factors? So the basically the low pass response is something like this, correct? And this node over here is basically increasing as the quality factor of our system is keeps on increasing. So this is basically equal to q. If this is 1, the magnitude response at omega naught is equal to q. Okay. So what if we put a high quality factor up front? So what will happen is first biquad will have some response. The second biquad will be this multiplied by the biquad's second biquad's response, and so on. Okay, so if in the beginning only you put high quality factor biquad, so what will happen is, in order to reduce so this will go greater than 1, right? So if this goes greater than 1, in order to reduce its peaking, you will have to reduce the gain at the DC. Okay, that is the only way you can achieve you can achieve this peaking to be less than 1. So in that case, what you are doing in first biquad only, you are reducing the amplitude of the signal. Now if you reduce the amplitude of the signal upfront, what will happen? Let's say the second biquad is giving some noise, okay, and this is the signal that is going in. Uh, so this is the noise of the second biquad, and there is the first biquad. And since you have reduced the gain over here in order to achieve the maximum peaking as 1 in this biquad, what will happen is this signal will attenuate. So the noise the second biquad is going to give is going to affect the signal more and more higher. So what you don't want is, or you don't want attenuation just at the beginning of your signal chain, because if let's say the gain of this was 1, in that case the signal that you would have got over here would be just the original signal. But now if the gain is so if the gain was 1, you would have got this signal. Now if the gain is, let's say, less than 1, that is the case if you put high quality factor biquad initially. In that case, you will get a sinusoid that is attenuated, and the noise of the second biquad will affect it more. Do you get my point? Hello?
Yes, sir. Yes, sir.
Yeah. So you don't want to put 0.707 quality factor first. You should always put the lowest quality factor first. That is 0.518 you will put at first. Then you will put 0.707. And at the end, you will put 1.932. So this is the correct order of placing the biquads. Or the higher the quality factor, you will place it at the end. In this case, what will happen? So we will see. The first biquad will do something like this. Why it will go down? Because its quality factor is very low, so you won't see any peaking. Now, second biquad will have a lesser amount of attenuation over here than the first biquad, but their overall multiplication will be Q1 into Q2. Now this is 0.707 into 0.518. Now this already has become much less than 1. So over here, when 1.932 gets multiplied with these gains, it still won't be able to peak outside greater than 1. So in this case, you won't need to reduce the gain of DC gain of the signal, DC gain of the last biquad, or any biquad for that matter. So in this case, you will get the maximum signal to noise ratio that can be possible. Do you get my point?
Yes, sir. Yes, sir. Good.
Okay. So having said that, we know now the order of the quality factors, that is 0.518 should come as first, then 0.707, then 1.932. And other thing to keep in mind is you should not do dynamic range scaling of individual bytecodes. You should always do dynamic range scaling of the cascade of bytecode. So you should first design all these filters, put them in cascade, and then see what dynamic range scaling you will have to do. Because let's say you do dynamic range scaling of individual bytecodes. In this, what will happen is the magnitude response of this bytecode will look something like this. Okay, individually. I'm not talking about cascade. Individually, it will look something like this, and you will think that okay, since this peak is going above one, so I should attenuate it a little bit. But in practice, what will happen when you cascade all these biquads, due to the attenuation at omega naught due to previous biquads, its peak would have already reduced. So in that case, you would not need to attenuate this. You will not need to dynamic range the scale, the last bytecode to an extent that you were doing initially. So doing dynamic range scaling of individual bytecode is actually suboptimal. The reason is that there you won't be getting the benefit of the attenuation that you are getting from the previous cascades. Sorry, cascades. Are you getting my point?
Sir, for bytecode 3, no dynamic range scaling, sir.
So that's what I'm saying. The solution that you showed, you did
Hmm.
dynamic range scaling of each bytecode individually, right? You designed the bytecode, you
Yes, sir.
did the
Yes, sir.
dynamic range scaling, and then put it. So if you
Yes.
do it that way,
For
you are
for
ending up
bytecode 3, hmm, hmm,
1 by
yes, sir.
1.932. So the Q resistor will become 0.518 in your case, right?
Ah, yes, sir. The in
Yeah.
bytecode 3, that resistance value will get decreased, the capacitance will increase. What I thought
So
that
518 ohms,
vector is
518 ohms it will be, right? Sorry, 5.18 kilo ohms it will be, right?
yes, sir. It will decrease, sir. Ah, yes, sir.
Yeah, so that's what I am saying. Here, the problem in this is you are basically doing the dynamic range scaling pessimistically, because if you do it individually, you will see this peaking. But if you cascade these three biquads, this peaking will go away. So in that case, you would have to do lesser dynamic range scaling than what you did at this point of time. Are you getting this point?
Yes, sir. Yes, sir. Exactly. Sir, for
Yeah.
the bytecode 3, you do the product of 3 also, sir. The quality factor.
Sorry. Yeah, for product of three. And what will be the product of three? Can you tell?
Yes, sir. Sure.
No, you don't need to calculate it. You should have this. So I told you, right? The quality factors of the biquads in a Butterworth filter are chosen in such a way that their product is always 0.707. So the product of three will be
Yes, sir. Point
0.707.
seven.
You can see this is 0.707, and
Yes, sir.
if you
Exactly.
take a closer look, this is basically reciprocal of this guy. 0.518 and 1.932 are reciprocal of each other.
Hmm.
Okay, so if you multiply this, you will end up with 1, and overall you have 0.707. So you will see always in this case, for example, if you design a
Hmm.
first order bicquad, sorry, it's a second order bicquad, in that case, you will see a quality factor of 0.707 itself. Okay, 1 by root 2, correct?
Sir, please take some marks, sir. Is there
Sorry,
any chance, sir?
sorry. Yeah, regarding marks,
Actually, I get a steps mark, sir. What I did now.
those you can mail it to the
At
these
least
kind
I'm
of
somewhat,
guides.
sir.
That's what these the marking scheme and all are decided by the other TAs and professor itself. So if you either you can wait for the assignment grades to be out, or you can mail if you have any queries, or if you have any contradictions on whatever grading you have, you can mail it, you can put it in the forum, that will be taken care of. So I can't comment on whether you would get step marks or not right away. So that basically is not decided by me actually.
So when they will reach that? Means that
Sorry,
sir not getting this will be released. Is there any
your voice is breaking. Can you repeat, or maybe you can type?
your score is not getting?
Sorry, come
The
again. I
code is
couldn't
not
hear
getting,
what.
sir.
So you are saying the
Assignment.
can you please type what you are saying? Your voice is breaking. So this okay, Shari, by what time will they be out? So before end of this week, you should be able to get the scores.
Every week from week
Sorry.
one onwards.
Uh, yeah, all the
From week
assignments
one
that
onwards, sir. Week
yeah
one.
yeah yeah all the assignments that you have submitted by end of this week, you will get the scores on. Yeah. So you can retry
Thanks, sir.
doing this. You can retry doing this assignment once again by the inputs that I have given. And then if you still have doubt, you can ask that in the next session. Any other doubts?
Sure, sir. Thank you, sir. Nothing, sir. Sir, at the end of exam, how it would be, sir?
Your voice again broke. Can you
MCQ
please
or
repeat? That actually I don't have the idea. I will confirm with other TAs and let you know.
yes, sir. Sure, sir. Means particularly the course only we are manually writing and submitting the course or MCQ
So that's
examination
what
also. Without,
I don't. I think it will be subjective, but I am not sure.
okay, okay, sir. Thank you, sir.
Okay. So I hope this issue is clear to you and all other guys who are on the call. So we will now. Since this is done, so this was basically a recap problem. Now we will move on to the this week's content. So this week's content was so this was week 5. In week 5, we were taught about the finite bandwidth of op amps and its effect on the biquad. So we had this omega u by s kind of transfer function, omega u by s kind of transfer function for the op amp, and using this, basically we tried to make the biquad and saw its effect. So how did we proceed for doing that? We basically put this op amp in the integrator with some UGB of 1 by RC, and this was omega u by s, and we did the math and the approximation that 1 by RC is much smaller than omega u. With this approximation, by doing the math that was discussed in the class, we got this transfer function as 1 upon SRC plus 1 upon S by omega u. Is this correct? Can someone confirm? Okay, so yeah, this was the transfer function that we got. And then we said that since h of s, we replaced it by h of s into 1 plus s upon omega u. And for finding the magnitude response, we replaced s by j omega. So basically, our j omega axis deviated from j omega to j omega minus omega square upon omega u, right? So this was something like this. So if the pole, let's say, was over here, in this case, this was 1 upon 2q omega naught. This was it, right? 1 upon 2q omega naught. So the quality factor, that was the enhanced quality factor, was this distance, and this distance came out to be so from this distance, basically we calculated the enhanced quality factor. So q hat was equal to q upon 1 minus 2 omega naught q upon omega u, correct? So this was the drill we did in this class, and then we said that we can use q enhancement and other techniques to find the actual response. So we will try to verify this using SPICE simulation. So let's set up the simulation. So we will take some high quality factor. So let's say we are taking a quality factor of 5, and then doing the exercise of this. So let's say we want a quality factor of 5 and omega naught of let's say 100 megahertz, and the input resistance, let's say we want 10 kilohertz, 10 kilo ohms, okay, and DC gain, say 1. Okay, so how our op amp will look like, how our bipod will look like, we will have 10 kilo ohms over here. So we will have a capacitance over here, the Q resistance, (50 kilo ohms). Why 50 kilo ohms? Because this is equal to Q times R, and then we will have a inverter. So using this inverter, we will, just a minute. So these will be also 10 kilo ohms. And then again a 10 kilo ohm. And then the feedback resistor over here of 10 kilo ohm. So we have omega naught of 2 pi into 100 megahertz, correct? So can you do the calculation and tell me what will be the value of capacitance? So 1 upon 10 kilo ohms into this capacitance is equal to 2 into pi into 100 into 10 to the power 6. 1 upon 10 into 10 to the power 3 into this capacitance is equal to 2 pi into 100 into 10 to the power 6. So from here, we get the value of capacitance as so this is 1 upon 2 pi into 10 to the power minus 12. And what is 1 upon 2 pi?
0.159 picofarad, sir.
0.159 picofarads. Okay.
Yes. On fire.
So these are the values that we got. We got this equal to 0.159 picofarad.
Yes, sir. If it is
And this
input
also
resistance is 10 kilo ohms. If it is 1 kilo ohm, it would be 1.59.
correct. So we are assuming 10 kilo ohms. So we will go ahead with this. So let's come to the simulator for this.
So, sir, sir, previous problem I have small doubt, sir.
Okay.
Sir, while you're calculating that frequency, no, sir, you're declaring that frequency range, no, sir. While frequency what
Sorry, come again.
in
The
the previous
frequency range.
question you already. Yeah, the frequency range in the question is declared as 0 to 50 kilohertz, no, sir. The peak
Okay.
response would be at 50 kilohertz, 50 kilohertz only, sir.
No, peak response won't be at 50 kilohertz. The bandwidth in that question was 25 kilohertz, right? So why will you have peak response at 50 kilohertz? Till 50 kilohertz, they will be falling with so it's sixth order, it will fall by like minus 120 dB per decade or something. So you won't find peak response at 50 kilohertz. The peak response you will find near omega naught itself, and that was 25 kilohertz. The peak the 50 kilohertz is just to like show that yeah, after the omega naught your response of the filter is falling. Do you get it?
Yes, sir. Yes, sir.
Okay, so let's try to build this op amp, sorry, the biquad. So my screen is visible, right?
No, sir.
My screen is not visible. Just a minute.
No, sir. No. Sir, can you do in LT space only, sir? LT space is very convenient, sir. Last time I found
uh,
found it.
Yeah,
Is there any?
actually, I don't have the access to LT Spice right now. So for now, I'll be doing it in Cadence. Like you can do the exact same things, just the commands will change. Apart from that, you can do those things in LT Spice as well. But right now, I just have Cadence. Sorry for that.
Oh,
So we will first of all start building. We will have a resistor. So a 10 kilo ohm resistor, then an op amp. So initially we will have so we will put a very high so we will have this op amp with the transfer function of omega u by s. So this will provide it. let's call this the ground connection. Then we have the capacitance, and the capacitance value that we found was 0.159 picofarad. And the quality factor resistance will be 50 kilo ohms. Then we will have the inverter. So for inverter, since we are using ideal op-amps only, so we will have only one voltage controlled voltage source with very high amount of gain. Sorry. So and this is 10 kilo ohms. So you guys are able to see my screen, right?
Yes, sir.
Okay. Okay, now we have the second op-amp. And the capacitance is the same as before. And on top of that, we have this feedback of 10 kilo ohms. So we will name the input and output nodes also as V in and V out. Now we will place the voltage sources. So there will be one voltage source that will have 0 DC voltage and will provide an AC magnitude response of 1. So we connected over here. And since here I have named all the nodes as AVSS, AVSS, and AVSS, so these all nodes are connected. So what I will do, I will have a common ground for all those things. So I will create one common ground. How will I create that? So I will have a ground voltage, then a DC voltage with zero voltage, and this will behave as a ground. So this is our bipod, and with bipod we have this as our ground. So if we try to see the net connections, so you can see with the pink line, you can see that all the grounds are connected, and this is the input source, and here we will be taking the output. So let's come to the simulator. So initially, let's say we have a insanely high frequency. So 100 megahertz is our this thing. So can anyone tell? Can anyone recall what was our condition for the UGB of the op amp? So basically, how I have created it, I will show. There is a uh, element in Cadence called SVCVS, with which you can implement the transfer functions. For LT Spice, you can do the following thing. So let's say you want to create some omega u by s kind of transfer function in LT Spice. What you will do is you will have, let's say, a voltage controlled current source. Okay. And its voltage So I will show it in the on paper first, and then we'll come back to simulator. So is my screen visible now? My paper screen.
Yes, sir.
Okay. So how do we create this kind of transfer function, this omega u by s kind of transfer function in LT Spice or Cadence? So either you can have, if your simulator has that, you can use some SVCVS kind of element. But if you don't have it in your simulator, what you can do is you can have a voltage controlled current source. So this is grounded with some GM. Okay, and this goes into a capacitor with some value C, and then after that you can have a voltage controlled voltage source. Okay, so if you give input over here as V in, the current that will be flowing out of this capacitor will be so the current flowing will be V in times GM in this direction. Okay, and this will since this is impedance is tending to infinite, so this impedance is infinite, so all the current will flow through this capacitor. So the voltage over here will be minus of V in times GM by SC. Okay, and since this is a VCVS, we will have its voltage gain as 1. So at the output we will have V in times S time and this multiplied by GM by C with a negative sign. Why negative sign? Because current is being pulled out of this capacitor. So with this, basically, if we set the values in such a way that we have some omega u, so for example, GM you can fix to or capacitor, let's say you fix to say 1 farad. It's not practical, but since you are building the ideal model, you can use it. So let's say the capacitor you set to 1 farad. So and you want some omega u. So GM you can put as omega u. Okay, omega u Siemens. So in that case, the transfer function that you will get is V in times S into omega u with a negative sign. So this, so mind it, this I am showing with the direction of the voltage controlled current source that is pulling out the current. So this you should keep in mind. With this, you will get the inversion also, and if you use, you can now use it directly in you can now use it directly as the op amp, because since you have the inversion, you already have the negative feedback. For example, if let's say this arrow was in this direction, in that case you won't get an inversion directly. In that case, what you can do is you can have a gain of -1 at this VCVS, and hence you can get the inverted, you can get the transfer function of omega u by s as intended. Is this clear to all of you? So I hope this is
Yes, sir.
so yeah. So this is how you can build this. So when you will be trying it for your assignments, or maybe with for your own curiosity, this is how you can build the transfer function omega u by s. So let's get back to the simulator now. So my screen is visible now, right? The cadence screen. Hello, hello. My cadence screen is visible, right?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So this is this is so in my case I have this SVCVS, so I'm using this. So like I have implemented. So I have put like I can put some value of omega u over here and get the intended quality factor. So first of all, let's put it at some insanely high value, so that we can show what is the ideal transfer function, and run the simulation. Okay, so plot it till, so 100 megahertz we have taken as bandwidth. We will plot it till 1 gigahertz. So that, okay, so again the thing is good. So you can see over here. So the DC gain is 1. I hope you can see it. I will make it a little wider so that it's clearly visible. So this is the magnitude response that we are getting. The DC gain is 1. So that we intended for, and at 100 megahertz we have gain of 5 that is equal to Q. So we intended for quality factor of 5, and that we are getting over here. So this is basically what we wanted, and we got when the bandwidth is infinite. So we will try to do it for let's say a finite bandwidth. So since our omega u is 100 megahertz, so and your quality factor, the omega g should be much greater than 2 times q times 2q by 2q into omega naught, correct? So 2q by omega naught comes out as 1 gigahertz. So let's say we have 10 gigahertz as our this thing. So So in this case, you can see the Q enhancement clearly. So where should it go? So from 100 megahertz into 10, just a minute. So okay, so this should be 2 pi into 10, not 10. Sorry for that. So here you can see the revised transfer function. So I will try to plot both the transfer functions one by one so that we can check it. So we will do a parametric sweep. So we will have two values. One is the ideal value, let's say some 1000 gigahertz. So this will give us the actual transfer function, and other is so 10 times. So we had basically the omega u should be the omega u of the op amp should be 2q times omega naught. That should be much greater than that. So for now, we will choose this 2q times omega naught, like 10 times 2q times omega naught we will choose. and we will see. Our quality factor is 5. Our omega naught is basically 2 pi into 100 megahertz. And basically what omega u we will have to choose is 2 times 5 times 100 megahertz into 2 pi into 10. So what it comes out to be 2 pi into 10 gigahertz. So this is what we will have. So these two things we will run and see for ourselves. So these are the results that we got. Okay. So let's bring these to the paper, and there we will try to analyze the results that we got. So what all did we have? We had Q as 5. We had omega naught as 2 pi into 100 megahertz, mega radians per second, sorry. And our omega u, we decided to be 2 into q omega naught into 10. Okay. So what quality factor, new quality factor should we have expected? It should have been q divided by 1 minus 2q omega naught divided by omega u. Okay. So this comes out to be q by 1 minus 1 by 10. And this roughly, so this basically comes out as q by 0.9. So our q was 5. So 5 by 0.9. Can anyone do the math and tell what is 5 by 0.9?
5.5. 5.5.
5.555.
Yeah, 5.5. So if we see over here, the yellow curve that we have is basically the ideal transfer function that gives us 5. And the red curve that we have, basically you can see it is approximately, since we did a lot of approximation while calculating it, so it won't be exact, but you can see it's close to what we calculated. So is this exercise clear to everyone?
Yes, sir.
Yes.
So any doubts in this till now?
Sir, like you mean what? In which way you're solving means how can we solve in the same way, sir, without committing any mistakes? Is there any reference book, sir?
So this you need to do with practice. you need to practice a lot, and then only you can achieve it. You should practice your own problems. Then, since you have the spice simulator, you can create problems by yourselves and verify them with spice. With this, you can get a lot of practice.
Means that problems and all, if they have set up for problems, means I can practice myself.
That's what you so for example, you want to design as many bipods as you want. So you have, let's say the question is there, that in that you were supposed to design, let's say, a sixth order bipod, and there sixth order Butterworth filter, and for that you did the equations. So let's say you want some more questions, so you can change the order to, let's say, 10, or maybe something else. For that you can decide the elements, do the dynamic range scaling, decide the order of the quality factors. So all these things you can do and verify it with simulator. And with that, basically, so what you will learn with this is, one thing is, definitely your accuracy will improve. Other thing is, you will learn the technique of debugging. For example, one of the nodes you are not able to understand by, let's say something you wanted, but you are getting some other value on that node. So in that case, what you will do is, you will start looking at from the first node itself. Okay, at the first node, this transfer function should be there. Are you able to get it or not? If you are able to get it, then so basically you will understand how to debug the solution, debug your mistakes. So all these things you will be able to do it. You can generate your own examples. You can calculate the values of components on paper. Then you can go to simulator and verify this. And if they are not coming, try to find the error where you are getting it. Once you find the error, this is also a skill to basically debug something that is not working. And this basically cannot be taught in a class or in a book. It's basically, when you do these things, you face errors and you try to debug them. So then only you will get to know all these things. So yeah, my suggestion will be generate your own examples and verify it on Spice.
So Shanti Pawan sir, one book is there, no sir. Active filter design there. Is there any chance to find your example, sir?
Yeah, there you can work
Delta
on that.
sigma converters.
No, Delta Sigma Converters is a book on a class of ADCs called Continuous Time Delta Sigma Converters. There you won't, I don't think you will find examples on active filter design. However, if you want to learn more on active filter design, there is a lecture series of Dr. Shanti Pawan that is like a design, with the same name. You can find it on YouTube. So there you can find more and
In
more
integrated circuit
architecture.
system, sir. In integrated group, sir, or
Yeah,
in NPTEL.
there you can find, or on YouTube, if you try to search active filter design by Dr. Shanti Pawan, you will get a lecture series. So in that you can find more. For example, the bipod that we did till now. The two op amp active RC bipod. This is actually known as Stowe Thomas bipod. This is a topology of bipod that is commonly used. There are other topologies of bipod that are present. For example, Sallen key, or maybe Rauch. So these kind of things also you can find in that. Or other way to implement the same Butterworth approximation is using GMC bipods. So there you don't use a negative feedback around loop and all those things. And a disadvantage with this is that you will have to have a op amp with such a high bandwidth. So you see here that you need some 10 times more than 2q omega not and then also you are like in some 10% error. So this is the disadvantage with this active RC thing, that you need to burn a lot of power. So to get more bandwidth, you will have to burn a lot of power. So there you will find one more topology called GMC bipod. In that, these constraints are not there. In that, there are some other issues. For example, the issue of non-linearity and all. So those things you will, if you take up those lecture series, you will get to know more and more topologies, and you can try all of those topologies on NT-SPICE and strengthen your concepts. And so with this, basically, you will have better accuracy also.
means while listening your lecture, professor lecture, the week 5 only I perform to the marks, sir. What I perform, somewhat I did. There also I come to mistake while you are saying that order. With the order itself, my confidence gets low, sir.
Yeah, that's what, like, it's not you will be able to understand this in a month or so. Like, you will have to practice for, let's say, a year or something, and rigorous practice. Like, this is just one of the aspects of designing, like doing calculations of component values, putting them like in simulator, seeing whether they are correct or not. So for this, only way is like practice. If you think that you are still not there, you will have to practice even harder. So for that, generate your own examples, verify it on Spice, and that is the best way to do it.
Sir, for analog IC design, that is different, no? So that is everything is pen and paper, right?
No, yeah, like analog IC design, initially it is all pen and paper, but they are also like, for example, you when you use actual model, there is a square law model of MOSFET. One is the square law model of the MOSFET. In that, basically, everything you can calculate with pen and paper. But those things also you can verify. For example, you are making a op-amp using a five transistor setup. I hope you know making a differential pair using five transistors. Do you know this?
No, no, sir. Till the week, what the compensation, the pole compensation, that one, no,
Okay,
sir.
so these are all these, and till now it's a block level only. So once you go to so even block level you can simulate and see pole compensation and all. You can do it. You can do dominant pole compensation, Miller compensation. You can
Hmm.
let's say you find the phase margin using calculations. Okay, you can actually build that circuit using VCCS. So since you build the circuit using transconductor and its output going to a parallel combination of resistor and capacitor, right? So you can
Hmm.
actually build that circuit in LT Spice, do the simulation, do the AC analysis, and see the loop response for yourself. So those things you can do. Do you know how to check the loop response in LT Spice?
No, no, sir. Few, this one, sir.
Yeah. So what you can do is, so for example, there is some. Just a minute. So what you can do is, so for example, you build a circuit like this. So let's say there is a two-pole system and it is dominant pole compensated. You have put some huge value of capacitance, some CC over here, and with this you have compensated it, and you need to find out the loop gain in the overall system. So what you can do is, so let's say this loop is in a inverting amplifier. Okay, so in this case, you will need to break the loop over here, right? So for if you have ideal models, in that case, you can just remove this connection, put a AC voltage source over here, and
Test voltage.
check the response at this node. This will give, and for that you will basically have to put a ground at this node input, correct? So
Yes,
you
sir.
can
Yes, sir.
check you can check the AC voltage at this node. Okay, this will work if your these models are made with like macro models, the VCCS and all those things. If you use, for example, if you make it with real transistors, in real transistors you need to provide some biasing. Okay, if you do this kind of stuff in real transistor, your biasing will get damaged. In that case, for LT Spice, what you should do is, so you know that an inductor behaves as a short for DC and a capacitor behaves as an open for DC, right?
Yes, sir.
Okay, so you can put a very huge value of inductance. Let's say 1 Henry. 1 Henry is a very huge value of inductance. And you can put a very huge value of capacitance. Let's say 1 farad. And then connect an AC voltage source over here. Now, when you have DC signals, for example, here you have to have some 600 millivolt for this, if this is made with some real transistors, let's say the circuit requirement is such that you need to have some 600 millivolts over here. And that is being provided when only when the circuit is in feedback. So in that case, for DC, this inductor will get shorted and this capacitor will get open. So this will behave in normal way and you will get the DC 600 millivolt over here. But for AC signals, now since this 1 Henry and 1 femtofarad are very huge, so in that case, what will happen is for very low frequencies also, this inductor will behave as open and this capacitor will behave as short. So in that case, for AC analysis, this inductor will go away, this capacitor will get shorted, and again you can plot the AC response over here and check the loop gain. So this loop gain, although will look something, so let's say the original loop gain was something like this. This will go something like this. Okay, now this part of the loop gain will depend on what LC value you choose. If you choose this LC value much higher, in that case, this will keep on making the ideal, like whatever loop gain you actually needed. Now to check phase margin and gain margin, you need to check the loop gain at near the unity gain bandwidth, right? So for that case, basically you can have some sufficient value of LNC over here and check the phase and magnitude response at omega UGB. So you can do is you can compensate it. You can make this model in LT Spice and check whether you are able to get the unity gain bandwidth and the phase margin that you calculated or not. And if you're not able
Yeah,
to
so
get it,
according
you
to
need
the
to
phase margin, we comment about stability also, no, sir?
yeah.
In
So
power
that's what
management.
let's say. Yeah, in power management also it is there. In analog ICs also it will be there. So you can check in both, and from this basically you can verify your calculations and all. Let's say you wanted 60-degree phase margin at some 1 gigahertz bandwidth, 1 gigahertz UGB. You do the calculation. Let's say for dominant pole, you find the value of CC. You put these values in the spice, and then you can see whether what you are doing is correct or not. So all those things you can do.
Sir, you are comfortable in power management also, sir? Power management in integrated circuits.
Like this tute is for circuit analysis for analog designers. You can take my email, and if you have some doubt, you can email me those doubts. I have some idea of power management circuits as well. So if I am able to, I will try to clarify your doubts.
Sir, can you write down, sir? The message is very slow, sir. Very slot size is very small, sir. Capture it. That is G only, no, sir?
Yes, okay, I will write it in the chat box.
That is G only, no, sir? G or S, sir?
S.
Oh, okay, sir. Yeah, perfect.
Dot. I'll write it in the chat box also. Like it's EE19D752 at. So I pasted it in the chat box also. I have pasted it in this also. You can mail your doubts on this. Or you are taking this PMIC course in NPTEL, or you are watching it from ICS Group's website?
No, sir, NPTEL, sir. Parallelly, I'm doing, sir. Open also.
Okay, so there you can post your doubts on forum also. Like the TAs of those PMIC NPTL can will reply back to you.
I mean, sir, like you not that much support to sir. That's why I they and they are not conducting live session also.
Okay, so fine. If you
I
can
can
try there,
interact
if
with you,
you
no,
are
sir. I can clear much. I will be very clear, no, sir. That's all.
that's what. So in these sessions, particularly, it's for circuits for analog circuit analysis for an analog designers course. So in these sessions, I will recommend you to ask the doubts based on this course only. But as far as other courses doubts are concerned, you can mail me on this, and I will revert back to you.
Yeah, sure, sir. Sure, sir. After completing
Yeah.
only one or two questions only, sir. Don't take more than 5 minutes.
Yeah, if it is too much necessary, we can have some Google Meets after this session. Someday, like there you can clarify doubts of rest of the subjects, like depending on the availability.
Yeah, sure, sir. Thank you, sir.
Yeah,
Sir, right now I'm doing three courses, sir. And three courses means while listening analog designers, it's very easy, sir. While implementing only facing
that's
very
what
difficult.
these are advanced level courses. These are not just theory courses. In this, you will basically learn techniques to this analysis is just to aid you in designing circuits. For example, this Q enhancement thing. For you do the analysis, you get to know that this much Q enhancement you are able to you are supposed to get. So with that, you can do design changes. For example, you can tolerate some Q enhancement of let's say some 10%. In that case, you know that you need to have your omega UGB of your op amp 10 times higher than 2Q omega naught. So these things will aid you in design. These things only you will be able to appreciate once you actually do it in simulators. So keep on doing it in simulators, and you will be able to manage.
But courses are advanced level only, sir. No,
Yeah. You should be well versed with like analog systems or
means I
maybe
part of
analog electron.
integrated system. I'm doing two more courses, sir. There I am getting full marks, sir. Out of 10 questions I'm getting, sir. Here only I'm putting much more effort, sir.
Yeah, so that's what like if you are not able to with the current level of practice, you are not able to get more marks, then increase your practice. That's what. That is how you will be able to perform better.
Thank you, sir.
Yeah. So okay, so we will continue with this example. So we see that this is the quality factor that we get. So what we will want to do is we will want to pre-distort our signal, pre-distort our just a minute. So we got the quality factor due to this enhancement as 5.5. Now what we will need to do, we will need to pre-distort our quality factor, that we will have to have some lower quality factor so that we can get back to quality factor of 5. So for that, what we will need to have, we will need to have a quality factor of 5 into 0.9, that is 4.5. In this case, even with an omega u of this frequency, so this is some 2 pi into 10 gigaradians per second. We will be able to get the desired quality factor. So let's try that also in the simulator. So here we make it instead of 50, we make it as 45. to get had the op-amps been ideal, your quality factor would have been 4.5, but now it will be 5 because of the calculations we did. So we will try to simulate it again and see. So you can see that your quality factor is restored to value around 5. Is this clear to you? So this concept of pre-distortion is clear to you? Okay, I will make the screen a little more wider. So you can see its value is now approaching 5. My screen is visible, right? My cadence screen.
Yes, sir.
Yeah, so I used Q resistor of 4.45 kilo ohms. So had it been an ideal op amps with infinite bandwidth, we would have got quality factor of 4.5. But since we wanted quality factor of 5 with the bandwidth that we calculated, so in this case, we used 45 kilo ohms, and still we got quality factor of 5. So is this clear to you?
Yes, sir. Yes, sir. Continue.
Yeah. So this was basically a live example, a simulated example of what we learned in the class. Any other doubts?
Nothing, sir.
Okay. So if there are no other doubts, so this was it from this session. Thank you for attending.